Hello, am I audible?
Yes.
Okay. Samara, end out from assignment.
Sir, actually, I didn't do it.
Okay. Due to lack of time or due to some confusion in it?
Both, sir.
Okay, good. So should I explain that?
Yes, sir.
Okay, just 1 minute. I think assignment was based on radiation. This one? This was the assignment?
Sir, I was not talking about this one. I was talking about that thermal, some conductivity maybe.
Okay.
Numerical part.
You have submitted this one for thermal expansion solid. Okay, just 1 minute. It was based on heat transfer.
Yes, sir.
This one?
Yes, sir.
Okay. In first part, heat is flowing through a rod of 25 centimeter long, having cross-section area of this much. Coefficient of thermal conductivity, K, is 9.2 in 10 to the power minus 2 kilocalorie per second per meter per degree Celsius. Temperature end of rod is 125 and 0 degrees Celsius. So in this, you have to calculate temperature gradient. What is the formula to calculate temperature gradient? Or what do you mean by gradient?
Change in temperature by length.
Good. So in this part, we have change in temperature 125 degrees Celsius and 0 degrees Celsius. So it will be 125 minus 0. Divide by length of that wire is 25 centimeter. So in terms of meter, it will be 0.25. So it will be 125 divided by 25 into 100. So it will be 500 degrees Celsius per meter. So it will be temperature gradient. Asma, is it clear?
Yes, that's clear.
Okay. The second part is the temperature of a point at a distance of 10 centimeter from the hot end. Suppose you have a rod having length 25 centimeter, in which this having temperature 125 degrees Celsius and this having 0 degrees Celsius, and its total length is 25 centimeter from this point to this point. So this temperature gradient, that is delta T by L, is from lower end towards higher end. So if you move along this path by any unit length, you'll get this much amount of temperature gradient. So you have to calculate temperature gradient at distance of 10 centimeter from hot end. That is at this point, which is at 10 centimeter from hot end. So from this cold end, it will be about 15 centimeter. Is it clear?
Yes, sir.
So temperature of any segment related to temperature gradient will be delta T by total length multiplied by X from that cold end. So delta T by L we have 500 and X length of rod from cold end is 15 centimeter. Divide by 100. So 0 and 0 will cancel out. 15 into 5, 75 degrees Celsius. Okay. Is it clear?
But they're asking to calculate from 10 centimeters.
So this will be the length at which we have to calculate. So from hot end, the length of this point will be 10 centimeter, but this temperature gradient delta T by L will define you from any cold end. It will be initial value and it will be final value. So it will be final minus initial. So we are calculating from lower temperature to higher temperature. So we have to calculate this much amount of length. Okay. That's why I have subtracted total length from 10 centimeter to get 15 centimeter. Okay.
Okay, sir.
Third part is rate of flow of heat. So it will be H is equals to Ka, change in temperature, divided by length. We have thermal conductivity, we have area of cross section, and we have calculated delta T by L. Put these values and simplify it. You'll get your answer. Aisha, is it clear?
Yes, sir.
Okay. Let me define you the second part. One end of a 2.5 meter long metal bar is in steam and the other is in contact with ice. A rod whose one end is at 100 degrees Celsius steam and the other end at 0 degrees Celsius connected with ice. If 12 gram ice melts per minute, so you have mass of ice to be melted, 12 gram, and time in which 60 seconds. So we have to calculate thermal conductivity for this process. Let me define the process behind it. You will say heat current will flow from higher temperature to lower temperature. So H equals to Q divided by T, which will be equals to Ka delta T divided by its length. This Q will be enough to melt this much amount of ice per unit time, that is 60 seconds. So in this part, ice is melting into water. So we can call this particular heat as latent heat of fusion. So Q will be equals to mass of ice to be melted times latent heat of fusion divided by time taken equals to Ka delta T divided by L. Samara, is it clear?
Yes, sir.
So from this expression, you'll be able to calculate the value of K since mass of ice is given, latent heat of fusion of ice is given, time is given, length, area, delta T, all quantities are given. Okay, just write it down if you want to. Done?
Yes.
Okay, in third part, the thermal conductivity of a copper is 4 times that of brass. 2 rod of copper and brass of same length and cross section are joined end to end. Let's say this is copper having same length is joined to brass. The free end of copper is at 0 degrees Celsius and brass is at 100 degrees Celsius. Calculate the temperature of junction. So Myra, which type of combination is this? Series or parallel? Asma, which type of combination is this? Series or parallel?
So series
Good. So heat current will flow from which side to which side?
from copper to brass, from brass to copper.
Good. So let's say heat current in this part will be H1 since it having higher temperature, and towards this direction H2. Temperature of this particular junction is T0. So H1 is K of brass A delta T, that is 100 minus T0 divided by length. Heat current in copper will be K copper area change in temperature T0 minus 0 divided by length. Since this combination is series, so heat current will be same for both. So H1 will be equals to H2. Now Kc A divided by L T0 minus 0 will equals to Kb into A divided by L, temperature difference 100 minus T0. A by L cancel out. Thermal conductivity of copper is 4 times thermal conductivity of brass. So it will be 4 Kb T0 equals to Kb 100 minus T0. So Kb and Kb will cancel out. So it will be 4 T0 equals to 100 minus T0. So 5 T0 will be 100 and T0 will be 20 degrees Celsius. Samira, is it clear?
Yes.
Similarly, you may find question number 4 as well. Okay, any doubt? Aisha? Okay. In last class, we have done radiation on the basis of which I have defined you Kirchhoff's law of radiation up to this part. Next is Stephen's law of radiation. It states, according to proposed hypothesis, which simply explains about every object which having temperature greater than 0 Kelvin will emit as well as absorb radiation at all time. But how much energy will it radiate and by what factor it may depend upon their temperature, you will be unable to explain that. So it will be explained by Stephen's law. It says emissive power of any black body at a particular temperature T will be directly proportional to fourth power of their absolute temperature. What do you mean by emissive power? Emissive power is amount of radiation emitted per unit area per unit time, which is also termed as intensity of emission of that body. So according to Stephen's law, the energy radiated by a black body per unit area per unit time is directly proportional to the fourth power of their absolute temperature. So emissive power is energy emitted by black body per unit area per unit time, directly proportional to fourth power of their absolute temperature. So if you remove this proportionality sign by any constant term, so it will become energy emitted divided by area times time equals to some sigma T to the power 4. This sigma is called Stephen's constant, and it is equals to 5.67 into 10 to the power minus 8 watt per meter square Kelvin to the power 4. Asma, any doubt related to Stephen's law?
No, sir.
Okay, just write it down. Just 2 minutes. Okay, you all have done?
Yes, sir.
Yes, sir.
Yes, sir.
Okay, so this is amount of energy radiated per unit area per unit time. We may write this expression as intensity. So on the basis of this formula, it will be intensity. Energy per unit time is also termed as power divided by area. Next is energy divided by area multiplied by time equals to sigma t to the power 4. So on the basis of this expression, you will be able to calculate energy, power. So power will be equals to sigma into a t raised to 4, and energy radiated will be sigma a time t raised to 4. So on the basis of this expression, you will be asked, let me define your question. Two black body at temperature 2 to 7 degrees Celsius and 7 to 7 degrees Celsius. Find ratio of their emissive power. In the same part, if a ratio of their radii is 2:1, find ratio of power radiated. Try to solve using the above formula. First, convert each temperature in terms of Kelvin, then put their values according to the formula. Otvika Kakumudi, are you there?
Yes, sir. Hello, sir. Can you hear me?
Any doubt related to this part?
No, sir. I'm understanding.
I have just messaged you something. Just reply. Sumaira, any problem while solving?
So can you give some hint?
Okay. We have this temperature and this temperature. So first convert it in terms of Kelvin. And since you have to calculate ratio of emissive power, which is nothing but intensity. So write I1 proportional to this part, I2 proportional to this part, sigma and sigma will cancel out. So you're left with T1 divided by T2 to the power 4. Okay. Suppose T1, if you convert it into Kelvin, 273 plus 227, you'll get 500 Kelvin. And for T2, 273 plus 727, you'll get 1000 Kelvin. Samara, is it clear?
Yes, I did this.
So emissive power is nothing but intensity. So intensity 1 divided by intensity 2 will be equals to sigma T1 to the power 4 divided by sigma T2 to the power 4. Sigma and sigma will cancel out. So you're left with T1 divided by T2 whole to the power 4. Put the value of T1 and T2 and simplify it. Okay.
Okay.
If you put the value of T1 to be 500 and T2 1000 whole to the power 4, so 500 in 2 times will become 1000. So it will be 1 by 2 whole to the power 4. So it will become 1 by 16. Okay, Samara?
Yes, sir.
Asma, any doubt? Now in second part, you have given ratio of the radius is 2:1 and you have to calculate power radiated. So use this formula, power divided by power equals to sigma area of first black body. So it will be 4 pi r1 square t1 to the power 4 sigma 4 pi r2 square t2 to the power 4. Sigma sigma cancel out, 4 pi cancel out. So you're left with r1 by r2 to the power 2 and t1 by t2 to the power 4. Just put their values and simplify it. Otpika, is it clear?
Yes, sir. Sir, will you, like, when are you going to start this, like, the fluids lesson?
We are doing thermal properties of matter, the last part.
Yes.
Then we'll start thermodynamics after it in this class or in next class.
Okay, sir. Thank you.
Samara, you got an answer?
Sir, I'm done.
We have R1 divided by R2 is 2:1. So if you put this whole square, T1 by T2 is 500 divided by 1000. So it will become 1 by 2 to the power 4. So 2 by 1 on squaring will become 4 by 1. 1 by 2 on fourth power give you 1 by 16. So in total, it will be 1:4. Is it clear?
Yes, sir.
Okay. Next is Newton's law of cooling. It says, suppose a hot body is kept in any cold surrounding. Suppose this is any hot object at temperature T and is placed in any cold surrounding at some temperature T0. So according to proposed hypothesis, you will say this hot object will radiate emission in all direction according to its temperature. since it having large temperature, so it will radiate more as compared to surrounding. But surrounding will also have temperature greater than 0 Kelvin, so it will also radiate, but some lesser amount of radiation like this. So during this interaction, there will be some net flow of radiation from hot body to cold surrounding, which result in decreasing of temperature of that hot body, which is called Newton's law of cooling, or which is defined by Newton's law of cooling. So in this part, I have just consider a hot body, which is not black body, at temperature T is placed in cold surrounding T naught. So there will be two different directions of flow of radiation. So one is from hot body. So intensity of radiation due to this body will be epsilon sigma T to the power 4, and it will be outward direction. Similarly, intensity from surrounding will be epsilon sigma temperature to the power 4, and it will be inward to that particular object. So if you have to calculate net intensity flow, so I net, it will be difference of these two terms. So epsilon sigma being constant, take it outside, T to the power 4 minus T naught to the power 4. Just 1 minute. In the above part, in case of Stephen's law, I defined you emissive power intensity for any black body. It is sigma T to the power 4. According to the relation of Kirchhoff's law, which says emissivity is a ratio of emissive power of any ordinary body to the emissive power of black body. So from this part, if you have to calculate intensity of that body, it will be equals to epsilon times intensity of black body. So it should be equals to epsilon sigma T to the power 4. That's why I've written this part multiplied by epsilon, this part multiplied by epsilon. Samira, is it clear?
Yes, sir.
Asma, any doubt?
No, sir.
Okay, just write it down.
So what is before sigma?
Epsilon.
So can you see this pen?
Just 1 minute. It defines here emissivity. Just 1 minute. Let me show you. This term. Okay. Samara, is it clear?
Yes, sir.
Okay.
Done, sir.
Now let me simplify this particular part to calculate rate of heat lost by this hot body. We may write intensity as energy dq by area by time equals to epsilon sigma T to the power 4 minus T naught to the power 4. Newton's law of cooling is valid for temperature difference between body and surrounding less than 100 degrees Celsius. So delta T is less than equal to 100 degrees Celsius. Let's say delta T equals to T minus T naught. So T equals to T naught plus delta T. Put the value of T by T naught plus delta T in this expression. So you'll get dq by dt equals to epsilon A sigma T naught plus delta T in place of T whole to the power 4 minus T naught to the power 4. Epsilon A sigma being constant. Take out T naught outside. So you're left with T naught to the power 4 bracket 1 plus delta T by T naught whole to the power 4 minus T naught to the power 4. Let me define you this part. Just multiply this by T naught and divide by T naught whole to the power 4 minus T naught to the power 4. And then I have just take out T naught as common from both these two parts, and on multiplying to the power 4, you will get this expression. On further simplifying, according to epsilon A sigma, T naught to the power 4 being common, so you're left with 1 plus delta T by T naught whole to the power 4 minus 1. Now using binomial expansion, we may write 1 plus x to the power n equals to 1 plus n times x when x is very small as compared to 1. So this expression will become epsilon A sigma T naught to the power 4 1 plus 4 times delta T by T naught minus 1. So 1 and 1 will cancel out. So you're left with 4 epsilon sigma A T naught to the power 4 multiplied by delta T by T naught. T naught cancel out. On putting the value, you will get 4 epsilon A sigma T naught to the power cube times T minus T naught. So Myra, is it clear till this part?
Yes, sir.
Aisha, any doubt?
No, sir.
Okay, just write it down. Just 1 minute.
Done, sir.
Done, sir.
Asma, done?
Yes, sir, done.
Okay. Now in this part, we have just derived an expression in which left hand side is dq by dt, which is also termed as rate of heat lost by the body, that hot body. This entire term is being constant for epsilon, area, sigma, and its temperature of surrounding. And this part is temperature difference of body and surrounding. So we can say a rate of cooling or rate of heat lost by a hot body when it is placed in a cold surrounding is directly proportional to the temperature difference of body and surrounding. This is rate of heat lost. This is any constant, and this is temperature difference between body and surrounding. So according to Newton's law of cooling state, when a hot body is placed in any cold surrounding, the rate of heat lost by it will be directly proportional to temperature difference of body and surrounding, which I have just proved. You don't need to prove this particular part for your school examination. I've just proved to show it and nothing more. So according to Newton's law of cooling, it states when a hot body is placed in cold surrounding, the rate of heat lost by the body is directly proportional to the temperature difference of body and surrounding. So Myra, is it clear?
Yes, sir.
Okay. So from this statement, let me define you some terms related to this expression. So you may write rate of heat loss proportional to temperature difference, that is T minus T naught. So rate of heat lost is dq by dt. And since it is being lost, so there will be negative sign. Removing this proportionality, put a constant term, which will be equivalent to this above part, 4 epsilon A sigma T naught to the power 3, and T naught minus this. This heat lost by that particular hot body will be responsible for changing its temperature from some initial to some final. So it will be termed as specific heat. So you will say, since this lost heat will tend to change its temperature, so it will be termed as specific heat. So ms dt divided by dt equals to, minus move to the other side, C times T minus T naught. Move M and S to right side and same quantity to one side. So you'll get dt divided by T minus T naught having same term, C divided by M into S, constant part, and you're left with this much. First, write it down to this.
Done, sir.
Done, sir.
Asma, any doubt?
No, sir.
You're written?
I'm writing, sir.
Okay. Done? Asma?
Yes, sir, done.
Okay. Now, on integrating both sides to find temperature, in left-hand side, we have dt by some temperature T, since T naught is being constant. So integration of this part will give you log, that is ln T minus T naught with some limit initial to final. This entire term will be constant, let's say K times T. Put the value of T to be upper limit T final. So ln T final minus T naught minus ln T initial minus T naught equals to minus of K into T. So on further solving, you will say ln final temperature equals to minus of K into T plus ln T initial, this part. So if you have to plot graph related to this expression, this will be termed as y. This is any constant term, initial temperature. This will be slope of that particular curve. So it is behaving as y equals to mx plus c. Y slope c. So graph of this particular equation will be straight line with some positive intercept and negative slope. So it will be like this. This is log T minus T naught versus time. Samira, is it clear?
Yes, sir.
Now, you'll be asked to define slope of this particular curve. Let's say this. So here in this part, slope is equals to K, which is equals to C by M into S. C was 4 epsilon sigma A T naught to the power cube divided by M into S. So related to this expression, you will say this slope will depend upon epsilon, that is emissivity, mass of that particular object, as well as specific heat. So greater the slope of this curve, it will have greater emissivity, but lesser specific heat constant. Is it clear?
Yes, sir.
Asma, any doubt?
No, sir.
Okay, just write it down.
Done, sir.
Asma, done?
Yes, sir, done.
If you may simplify this particular ln, that is natural log, if you remove this expression, let me define you. Suppose you have a to the power x is equals to any natural number n. So if you have to relate the exponential with base and n, it will be defined by log. So x will be equals to natural log or simply log to the base a n. If this base a is replaced by any exponential function e raised to x n, so it will become x equals to ln n or log to the base en. So in this part, we have ln, some quantity. So if you remove this particular term, you will get this part. That is exponential to this quantity. So on solving this part, t minus t naught, I've just removed this ln. So on opposite side, you will get e to the power this quantity, exponential function. So the graph of this particular function will be temperature difference with time. It will be exponentially decreasing like this. So you'll be asked, what would be the nature of graph for ln temperature difference versus t or simply temperature difference versus time? Okay. So for log, it will be a straight line, but for only temperature difference, it will be exponentially decreasing. Is it clear? Samara, any doubt?
No, sir.
Asma, should I repeat this log part?
Yes, sir, could you please do that?
Okay. Suppose you have 2 to the power 3. It will give you 8. 5 to the power 2. It will give you 25. So how to relate the exponential with this base part and that natural number 8? So I've just defined this, in which a is base and x is exponential to it, so that you will get number n, like a is 2 and exponential is 3. So 2 to the power 3, it will be 8. So if you have to calculate the exponential related to these two terms, it will be defined by log. So log is nothing but reverse of exponential function. Is it clear? Asma, is it clear?
Yes, sir, it's clear.
Now, in this log, you may take base to be any term, but if base is e, that is exponential function, which is numerically equals to 2.72, it will become ln, that is natural log. Is it clear now? Aisha, any doubt?
No, sir.
Done, sir.
Done?
Sir, did you call me?
Yes, you have written.
Yes, sir.
Okay. Now, this log term and exponential term will be very difficult to simplify it. So let me define you shortcut method to calculate or to solve numerical on the basis of this Newton's law of cooling. In this part, I've written ms delta T divided by T equals to some constant times temperature difference. So you'll write as dt divided by dt equals to minus of some constant K times temperature difference T minus T naught. So this dt is temperature difference. So it will be T final minus T initial divided by dt, that is time. So T minus 0, constant K. T is average temperature. So it will be Ti plus Tf divided by 2 minus T naught, temperature of surrounding. Since final temperature of body on cooling down will smaller as compared to its initial temperature, so just move it to left side and move this to right side. So you'll get negative sign here. So that negative sign and this negative sign will cancel out. So you will get T initial minus T final divided by T equals to some positive constant. T initial plus T final divided by 2 minus T naught. So this will be your final expression for calculation of Newton's law of cooling. So Myra, any doubt?
No, sir. Done.
Done? Let me give you a question related to this part and how to solve it. a body at 60 degrees Celsius is kept in surrounding of 10 degrees Celsius. It cools down to 40 degrees Celsius
Sir,
in, yes,
could you please excuse me for a second?
yes. Okay, Asma. So a body at 60 degrees Celsius is kept in surrounding at of 10 degrees Celsius. It cools down to 40 degrees Celsius in 5 minutes. Find time, cool it down further to 20 degrees Celsius. So in this part, we have a body initially at 60 degrees Celsius, decreases to 40 degrees Celsius, and further to 20 degrees Celsius. In this part, time is 5 minutes. In this part, time we have to calculate. Temperature of surrounding is 10 degrees Celsius. So break this particular segment into two parts. First, from this point to this point, and then from this point to this point. So for first part, we have initial temperature 60 degrees Celsius, final temperature 40 degrees Celsius, and time taken is 5 minutes. So it will be 5 into 60, that is 300 seconds. So if you put these values in the above formula, you will get T initial 60, T final 40, time taken 300, K, T initial 60, T final 40 divided by 2 minus temperature of surrounding 10. So it will be your first expression. Similarly, if you solve for the second part, for which we have T initial as 40, T final 20, and time taken, we have to calculate it. So if you put these terms to the above equation, you will get 40 minus 20 divided by time equals to K, 40 plus 20 divided by 2 minus temperature of surrounding 10. Now try to calculate the value of K from first equation, put it in second, you will get T. Okay? Is it clear?
Yes, sir.
Try to solve. Just solve. I'm coming in 1 minute. Good, Samaira. Advika, you got any answer? Or you are doing? Let me solve. 60 minus 40, it will be 20. Divide by 300. K. 60 plus 40, 100. Divide by 2, 50. Minus 10, 40. So this part and this part will cancel out in 2 times. So K will be equals to 1 by 600. Put this expression in right side. 60 minus 40, 40 minus 20 is 20. Divide by T, we have to calculate. K is 1 by 600. 60 plus 20. 40 plus 20 is 60. Divided by 2, 30. Minus 10, 20. This part cancel out. So T will be equals to 600 second, or in terms of minute, it will be 600 divided by 60, 10 minute. Is it clear, Aisha?
Yes, sir.
Okay. Now let me define you something related to this question. Initially, we have 60-degree temperature. So in 5 minutes, it cools down to 40 degrees Celsius. And in further 10 minutes, it reaches to 20 degrees Celsius. On going from 60 to 40, temperature difference is 20 degrees Celsius. On further 40 to 20, temperature difference is again 20 degrees Celsius. Now, but initially, the body was at 60 degrees Celsius, higher temperature. Further, the body has lesser temperature, 40 degrees Celsius. So you'll say on decreasing temperature, the rate of cooling of a particular object decreases. So to change the temperature by same amount, it will take longer time at lower temperature as compared to higher temperature. Is it clear?
Yes, sir.
So you will say at lower temperature, the rate of cooling of body decreases. So it will take longer time to change temperature by same amount at lower temperature as compared to higher. Aisha, any doubt?
No, sir.
Okay, just write it down.
Done, sir.
Then, sir.
Notpika, any doubt? Okay. Now there will be a question related to this part. Suppose you have a body initially at 100 degrees Celsius, changes to 90 degrees Celsius in time t1, further to 80 degrees Celsius in time t2, and further to 70 degrees Celsius in time t3. So how will t1, t2, t3 related to one another? Are they all equal to each other, or there will be something different relation in between them? Samaira?
They will be different.
Good. Which one will be smaller and which will be larger?
Smaller one will be T1 and larger one will be T3.
Good. Since initially object having temperature 100 degrees Celsius, so its rate of cooling would be fast, so it will take smaller time to change by same amount. So T1 will be least, then T2, and then T3. Okay, you all are done?
Yes, sir.
Now the last topic of this chapter is Wien's displacement law. Suppose a metallic rod, let's say iron rod, is placed on burner, which may have very high temperature. So on absorbing heat, it will tend to glow So which color do you observe first? Blue, green, yellow, violet, something else? Samira? Suppose an iron rod is placed over flame. So in which color it would tend to radiate initially?
Orange.
Why not red?
Yeah, orange.
Red. I think so. First red will come, right?
Okay, first red and then?
I guess then orange will come.
Then?
Mm. Then yellow.
Okay, good. Then?
So
And
is
just
it
red.
your one?
It will be like that. Let me define you why it is. Suppose a body which having temperature, so it will have energy as 3/2 kBT. Greater the temperature of body, it will have more thermal energy related to it. On the basis of which, it will tend to radiate and radiate electromagnetic radiation, or you will say in the form of photon. So energy related to photon will be hc by lambda. You must have learned this formula in chapter 2, structure of atom, for photoelectric effect in chemistry. I think so. Where h is Planck's constant, c is the speed of light, and lambda is its wavelength. So equate these two terms. So 3/2 kBT due to thermal energy converted in the form of energy of photon, so hc by lambda. Now rest of the thing is constant, only temperature is variable and wavelength is variable. So using this relation, you will say temperature and wavelength is directly proportional or inversely proportional.
Inversely proportional.
Good. According to the visible region, violet, indigo, blue, green, yellow, orange, and red, which one of radiation will have longest wavelength or shortest wavelength? Which one will be longest and which one will be shortest? Red is longest wavelength.
Is it red?
Okay, so red is longest and violet is shortest. And since according to this relation, temperature and wavelength is inversely proportional to each other. So initially, object will have lower temperature, so it must tend to radiate in higher wavelength. So all objects initially tend to glow as red. Is it clear?
Yes.
Yes, sir.
On further increasing temperature increases, wavelength decreases, so it will tend to go along this way. Asma, is it clear?
Yes, that's clear.
Okay. So let me define you this particular Wien's displacement law. It states the maximum wavelength of radiation emitted by hot body is inversely proportional to its absolute temperature. It means lambda maximum inversely proportional to temperature. So by replacing this proportionality sign, you will get constant. So lambda maximum into T equals to some B as constant, which is called Bean's displacement constant, which is numerically equals to 2.3 into 10 to the power minus 3 meter Kelvin. According to graph related to this part, wavelength versus temperature. Initially, it will have some lower temperature, so it will tend to radiate at higher wavelength. On increasing temperature, large wavelength for some small temperature, small wavelength for some high temperature. Samara, is it clear?
Yes, sir. Done, sir.
Done, sir.
Asma, done?
Yes, sir, done.
Okay. Let me ask you a question related to this part. Suppose 3 stars P, Q, R radiating as blue, red, and green. Orange temperature of their surface in ascending order. Just try to solve. Asma, just tell me which is longest wavelength in these three terms. Samara, you have to arrange the temperature of star. Yes, Asma?
So could you give me some time? I'm writing some part of the question.
Okay, okay. Samara, arrange your answer in terms of the temperature. Good. Aisha, just tell me which is longest wavelength
It's red.
and red corresponding to which star? Q.
It,
So temperature of star Q will be least. The next, green for red, and then blue, P. Is it clear, Asma?
Yes, sir.
Okay.
The answer is the most is B, then red. Then green, then red, right, sir?
No. Red having
As in
highest wavelength.
from yes,
So
sir.
it will have least temperature. Yes.
So red
Then
has the highest wavelength and will have the least temperature correspondingly.
yeah.
Then it's the opposite for blue. So it's in that order is blue, red, green, and blue, right?
Yeah.
Okay.
Atvika, is it clear? Okay. So let's stop here for today. This is our entire chapter, that is thermal properties of matter, which we have finished. So just revise this whole chapter and try to do problem related to this part. In next class, we'll start with thermodynamics. Okay.
Okay, sir.
Okay, then we'll continue in next class.
Thank you.
okay, sir.
Thank you.
Thank you, sir.
Thank
Bye,
you, sir.
Thank you.
Thank you, sir.
Thank you.